Welcome, and in this video course we are looking at the CyberOps Associate version 1 course. This course is going to cover the skills and knowledge needed for successfully handling the tasks and duties, responsibilities of an associate level security analyst working at a security operations center. The goal of this video series is to help prepare learners for the Cisco 200-201 certification that's focusing on understanding the Cisco Cybersecurity Operation Fundamentals course known as CBROPS. Module 12 is Network Security Infrastructure. So we're going to be looking at in this chapter are going to be things such as topologies, devices, and services. So in previous sections, we looked at network infrastructure, network devices. Well, here we're going to be looking at the security aspect of them. So network topologies are typically going to be how the network is laid out. We also need to talk about the mapping or the design or the overall structure. And what ends up happening is the network infrastructure is comprised of several different elements. In devices, computers, laptops, printers, wireless tablets, phones, things that end users are going to use. All of those are connected to some form of network media, wireless, copper-based or fiber optic-based media. This is what's going to allow the data signal to be transmitted between in-device and the overall infrastructure. The infrastructure or the intermediary devices are going to be things like switches, routers, firewalls. So I say infrastructure when we talk about intermediary devices, but in reality, infrastructure is going to be a combination of the entire network, not always just the intermediary devices. The key infrastructure are the routers and the switches, but the cables that connect everything are also equally important. The end devices that are connected to the intermediary devices are also equally important. So that is the foundation of infrastructure. But you also need to know three additional key terms. NIC, Network Interface Card. That's going to be the interface card that allows the device, the end device typically, to connect to the intermediary devices such as a switch. If it's a wired connection, you'd have a wire NIC. If you have a wireless network, you'll have a wireless NIC. If you have a mobile device, you may have a cellular NIC. If you have a Bluetooth network, it will be a Bluetooth NIC. The NIC is just the interface card that allows you to interface between your device and the network. Next are interfaces and ports. Where do you plug your device into? A physical connection, a physical port, or a physical interface, that's going to be the main staple when we're talking about a wired network. If we're talking wireless ports don't exist. Wireless interfaces don't exist. A wireless access point that we connect to is going to be more of the key thing there. Wireless access points are also going to be an intermediary device. When we put all of it together, we get either a physical topology or a logical topology. A physical topology outlines the physical layout of the network. Where are they physically located? What rooms? What location? With the logical topology, we may get what ports things are plugged into. We also may get what VLANs or what spheres of control we're connecting through. So physical is going to be the physical layout of the network. The logical is going to illustrate the ports, the addresses, the VLANs, things of that nature. A big thing is going to be what is the size of the network. So we can have a small network, we could have a home office network, we could have a medium or large network, or we can have a state or multi-state or a country or global network. So networks can be all different sizes. The nice thing is the overall characteristics are going to be the same. When we look at a local thing for communication, local communication is a LAN, local area network. And they connect to like the internet, or they connect to other networks through a WAN, a wide area network. And the nice thing with this is we see this all the time. You have a home network. You connect to the internet. Well, your internet provider, your ISP, your internet service provider, they actually manage a wide area network. That's how we're able to go from our resources locally to a web-based resource like Google or Amazon. Those are going to be other networks that are reachable through a WAN. Now, these are only two types of networks. There are many more, like a metropolitan area network, a MAN, and that's going to be more of a city-wide network. We could also have like a storage area network, a SAN, or a PAN, a personal area network. That could be like your mobile device in your car, or your mobile device and your Bluetooth headset. Those would be other forms of network types. But again, when we first learned about this, we learned about just the major two, LAN and WAN. LAN is going to be small, limited, kind of a single organization. A WAN is going to be a larger geographical area. They're going to have a service provider typically, and they can stretch for great distances and typically provide connections between two different LANs. The overall network design is going to be a three-tiered design, and this is typically what you'd find in switching networks. The switches closest to the end device will be access layer devices. The things that connect the access devices will be a distribution layer. They're going to be a little more expensive switches, but not the most high-end. And then we have our core level switches. Those are going to be the most expensive switches, and they may have things like multiple power supplies, multiple fans, things to make sure that they are not turned off. So why do we do this? Well, if we look at like a campus, for example, we can have that each floor, each classroom on a floor is tied to an access layer switch. Each classroom has the end devices. Each classroom connects to the building's main switch. That would be a distribution layer switch. Each building is interconnected to the main campus network through the core layer switches. From here, the core layer switches will go out to the internet. That's a typical three-tiered structure. When we talk pricing, the access layer closest to the end user, they're going to be the cheapest. They do not have the fastest links. They do not have the most feature-rich sets, where distribution is going to be a little more expensive, but they're going to have more features. They're going to have more filtering ability. They also may be a little faster. Then the core layer, they're going to be drastically more expensive. They're going to have a lot more features, but they're also going to be typically fewer in ports. That is because the core layer is made to handle the fastest amount of traffic. It's also made to process different features, where the distribution is made to offset some of that and handle some of the traffic filtering, and then we go down to the access layers. What you'll end up seeing is oftentimes a collapsed core. That is where the core and the distribution layers are combined. And then we have the collapsed core and an access layer. That distribution layer is completely gone. In reality, The distribution and the core switches can be combined. It's just a matter of how you design your network. And you'll notice here with this collapsed core, we have multiple links to our switches, ensuring communication. So what are some common security appliances or some common security architectures? Well, one of the big ones is anything coming from the internet going into the network, block, deny them. If the original request is coming from inside the network, so it's inside the network going out to the public network, the internet, then we can trust that. And then only responses to requests that are originated from inside the network would be allowed back in. That way, we don't trust things from the internet unless it is a direct response from something inside the network calling out and respecting or expecting a return response. For example, inside the trusted network, you may go to Amazon.com. Well, Amazon.com will have to go out to the public or untrusted network. What will happen is the untrusted network will route it to Amazon. Amazon will then respond with the appropriate response, and that will go back through. The router should receive that request going, hey, this resource is being requested by this internal trusted device. The router or the firewall should look at that and verify it, and if verified, should allow the access back in because it was originated from inside the trusted network. A few of the things that we don't really discuss are things like a DNS type zone or a DMZ type zone. When we're talking network infrastructure, we're going to talk about DMZs. DMZs are taken off of the core or the edge network device, whether it be a router or a firewall. What ends up happening is the DMZ is going to be anything that needs to be accessed by the internet that we don't want to be in our inside network. So we have this special zone set up so that the internet can access it and the internal can access it, but that way we still allow for a gap between the internet and our private or inside network. This is called a demilitarized zone, DMZ. Typically, these will be servers that need to have direct internet access, like a web server or an email server, but still need to be accessed by an internal-based resource. And it is directly off of the core network router or firewall, depending on how the network is set up. Since we're talking a firewall, firewalls can filter based off of different criteria. One way a firewall can filter is called zone-based policies, or ZPFs. Basically, depending on the zone you're in, you'll get a group of policies based off of that zone type. So you can have two internal networks, LAN 1 and LAN 2, and they can be similar in zone types. Different networks, but they can have the same policy attached to them. Where we have a different zone, like DMZ, that will be a completely different group of policies. This allows us to keep things more uniformed based off of whatever criteria we need. We have a packet tracer kind of showing the packet flow in a WAN and a LAN topology. This should get you familiar with the overall data flow. So now let's get into our security devices. So our security devices could be things like firewalls, and they are going to allow us to filter traffic. Firewalls are a set of rules, an access control list or an access control entry that outlines what's allowed to come through the network. And only what's allowed is what gets through the device. That's essentially what a firewall is. But we have other types of devices, not just firewalls. Also, firewalls have different types as well. Firewalls typically prevent the exposure of internal hosts. They're not made to stop everything, and so a big limitation is misconfiguration. When we're talking sanitizing data flow, really good benefit for a firewall. However, the firewall is assuming that application data is secured. So data from applications that can't be passed over firewalls securely is a growing concern. Another benefit is it does allow for blocking of malicious data from a device inside the network or even outside the network from transmitting vice versa. If you're inside the network, transversing out. If you're outside the network, coming in. The issue is things that initiate inside are typically allowed out. So a limitation for firewalls would be users might proactively search for ways around the firewall to access blocked material. If your company blocks YouTube, for example, people find ways around that and they circumvent the filtering software. Firewalls basically allow for better security management, but it does add a certain level of complexity. Another negative or limitation for a firewall is it will make the network run a little slower because we're filtering traffic, which means that traffic now then has to be inspected to ensure that they're meeting the policies. Firewalls typically operate at layers 3 and 4, and that's going to be a stateless firewall. Basically, that means that it's not going to pay attention to the overall state. So packet filtering firewalls are part of the router firewall. They prevent data for layer 3 and layer 4. There are stateless firewalls that use a simple policy that basically says either allow or deny based off a protocol. Problem is, what happens if you have an application that initiates traffic? That would be a stateful firewall because you want to see what data was actually calling out outside the network and being allowed back in. If we're only allowing certain traffic protocols, stateless, then there might be some issues. So stateful adds in that fifth layer, that session, because the session is going to be dealing with the application stack. The session is going to be looking to see if your web browser on the internal network called out to a public network like Amazon or Google. And if so, that traffic is allowed back in because there was an established session. We also have application gateway firewalls or a proxy firewall. They operate at layers 7, 5, 4, and 3. Basically, most of the firewall controls are filtering, and that's done through the software. Oftentimes, application-based gateway firewalls are looking at application-based data. We also have a new family of firewalls called Next Generation Firewalls, or NGFW. These are firewalls that are supposed to be the next generation. They go beyond stateful. They allow for additional layers of protection like IDSs and IPSs. They look at application and they're more aware of what type of data is flowing through the network. They also allow for better upgrade and upgrade paths for information, as well as other techniques that are used to address the ever-evolving security threat of a modern-day network. So I said things like an IPS and an IDS. We haven't quite talked about those yet, but basically they are additional filtering tools and they alert you based off a certain criteria. So we also have a few other types of firewall implementations. They could be things like a hybrid firewall. That's a combination of various types of firewalls. They could be a network-based firewall, or a server-based or host-based firewall. A network-based firewall is going to be something that's on the network. A host-based or server-based might be a firewall running on an end device. We can also have a transparent firewall, and that's just a way to filter traffic between different interfaces. So I brought this up earlier. IDSs and IPSs, intrusion detection versus intrusion prevention. Detection basically will alert you when something happens, but that's all it does. It just alerts you. An intrusion prevention system takes action. It will look at what's going on and it will respond accordingly based off of a pre-approved list of actions to take. An IDS, the detection portion, only detects and reports, does nothing else. The prevention system can be active, it will do something. So advantages and disadvantages between the two. An IDS does not impact the network. All it does is listen and report. The disadvantage is, well, it doesn't do anything. It doesn't trigger anything. There is no real function after it detects. You also have to really fine-tune the IDS. It does provide vulnerabilities because there are evasion techniques that can evade the sensor of the IDS. With IPS, there are trigger packets. They can use normalization techniques, what it thinks is normal. The disadvantage is it could overload the network. It does impact network latency and delay and overall bandwidth because the IDS has to be more active. It has to look deeper in all of the packets, so it does add an additional layer of delay on the network. Normally, they complement one another. IDSs and IPSs go together. Deciding which implementation is based off of your security goal and your budget. You can also have a hybrid IDS that's also an IPS. So it really all depends on the overall design of your network. Just like firewalls, you can have a network-based or host-based. A host-based is called a HIP, HIPS. A host-based IPS, again, is going to be on an individual host as opposed to the network itself. You can have a network-based IPS, that would be called NIP in IPS. You can have a host-based and network-based IDS as well. The advantage of having a host-based is it provides protection to the individual operating system. However, it is dependent on that operating system. That means you have to have a IPS on all machines. So that's a disadvantage. For network-based NIPS, that will be an appliance on the network that then will act accordingly. The sensors will detect malicious material, unauthorized access in real time, and take action that was pre-approved. So when we are looking at the overall infrastructure, we're talking security appliances, we also have to then talk about things like malware protection or web filtering or email protection. We have a traditional malware protection, anti-malware, antivirus. We also have web filtering. That could be a filter that prevents web content from being viewed. We also have an email security appliance or email filtering, and that allows us to look at email and prevent issues from coming from email. Phishing attempts or malicious links, malicious senders, things like that will be prevented by the email security appliance. Any type of web traffic filtering will be attached to the web security appliance, and anything tied to anti-malware or antivirus will be tied to the malware protection. So we've covered a lot of material, but we still have to talk about services. Services are key in the network. So when we say services, what do we mean? We're going to be talking things like the AAA service, authorization, authentication, accounting, SNMP. We're going to be talking about a SPAN, IDS. Those are services that are sitting on the network. We're also going to be talking about things like ACLs and ACEs. An ACL is an access control list made up of access control entries, ACEs. An ACE basically is a permit or a deny off of a certain criteria. For example, we can have an ACL going into R1 that says deny video to switch 1, also deny access to switch 2 from switch 1. That would be an example of two different ACEs that make up the ACL. And then there are rules about placement and how we can word those ACEs and ACLs. Essentially, ACLs and ACEs are just used to filter network traffic to allow, permit, or deny. ACLs have a very specific set of features based off of if they are a standard ACL or an extended ACL. A standard ACL only permits or denies traffic from the source. An extended ACL has different types of attributes. With an extended ACL, you can filter off of source or destination address. You can filter off of protocol. You can filter off of source ports, UDP or TCP, or destination ports. You can also then do a combination of protocol types for better control. So you can filter off of address and then include different ports to allow or deny if we are using an extended ACL. We have a lab covering the creation of an ACL. So we also had SNMP. SNMP is the Simple Network Management Protocol, and this is a family of protocols used to make up a platform used for simplifying management of network devices. Basically, you have an SNMP manager and you have an agent. The manager runs the management software, and they send set and get commands to the different agents. An agent is going to be a end device, a end router or a switch or printer or things of like that nature. And the manager will receive updates, traps from those managed agents. Those agents will respond with toner level of the printer or logs for a firewall or any type of additional data that might be needed based off of your network design. We also have Netflow. Netflow is tied to Cisco iOS because it's owned and operated by Cisco at the moment. That provides statistics on packet flow of the network. Netflow provides data for network and security monitoring, network planning, traffic analysis, and IP accounting for billing purposes. With cloud technology, the amount of data going through a third-party cloud network is typically billable. So Netflow is used to keep track of data flow for billing purposes. We also have port mirroring. This is going to be part of the span. Basically what we do is we allow for a port on a switch to be attached to a packet analyzer. And what ends up happening is, as normal traffic goes throughout the network, the span port will actually listen and clone or get a copy of all traffic so that the network analyzer or the packet analyzer can analyze and review all data. We also have a Syslog or a logging server. Basically, you can have all your devices dump the log to a syslog server for better log analysis. We also have a NTP or time management type server. NTP is Network Time Protocol. NTP allows for centralizing time management. This is done by organizing them into stratums. The top stratum is going to be some type of authoritative time zone. There are NTP time groups out there that are not government. They could also be large business or nonprofits. Those are typically the stratum time zones, the stratum 0 time groups. From there, we have a higher tier stratum 1, And essentially, they get their time from the stratum zeros, and then they allow for that time to be distributed to stratum 2s and stratum 3s and so forth. The stratums 2 and stratum 3s, that's typically where most businesses are going to be operating at. Basically, a stratum 2 is going to be receiving a time update from a stratum 1 so that we can verify overall time management. We have our AAA services: authentication, authorization, and accounting. Authentication is verifying that you are who you say you are. Authorization is verifying the permission that you have. You walk into a bank. How did the bank know that you are you? You, the individual, have a card, an ATM card, and a PIN number. So that is something you have, ATM card, something you know, PIN number, and maybe a biometric like a fingerprint, something you are. Those are the 3 key factors on authentication. Normally we look for 2 of the 3, but for better level of security, 3 of the 3 is better. Something you know, something you are, something you have. That way, that ensures authentication. Authorization is just verifying what you can do after they have verified your identity. Accounting is transactional. It's logging everything that you're doing. So when you go into the bank, when you put your ATM card in and you verify that you are who you are, you've been authenticated, what are you able to do? Well, maybe you're authorized to take $300 out of the ATM. Well, the accounting aspect of that would actually be logging you accessed the ATM. You withdrew money, and they verified that it was you. So there are different ways to handle AAA services. We can push that to a third-party server. It's typically a Radius server or a TACAX server. A Radius server is open standard, and it's going to be one of the more common ones. We have a TACAX server. That is a Cisco proprietary server. TACAX uses TCP for communication. Radius uses UDP. TACAX basically will encrypt the entire packet for confidentiality. Radius only encrypts the password. Accounting is limited with TACAX. Accounting is way more extensive with Radius type servers. The big thing here is that TACAX separates the different AAA according to the AAA architecture. Radius will combine authentication and authorization, but then they'll separate accounting. That's a really common test question. TACAX separates all 3. Radius separates authentication from accounting. Authentication and authorization are combined. We also have a VPN, a virtual private network, and this is what allows you to extend your internal network through a third-party network. Basically, if I want to extend the corporate network to my home users, I can through a VPN. It will encrypt the traffic and will allow me to emulate or simulate me being local on the network. Alright, so that is the end of this chapter. We talked about the overall representation of the network, looking at topologies, both physical and logical, addressing and general LAN design, the layers, access, distribution, core layers. We looked at boundaries for network traffic. We looked at firewall and firewall types. We looked at things like IDSs and IPSs, as well as malware and antivirus protection, web security, and email security appliances. We looked at ACLs. We looked at SNMP and Netflow and span for port mirroring. We wrapped it up with NTP, logging, and AAA based services, and we discussed at a very low level VPN connections and kind of their purpose to extend through a public network. That is all for this chapter. If you have any questions or concerns, please feel free to reach out. Thank you. If you have any questions or anything, please feel free to reach out. Again, with this material, being able to ask questions and discuss some of the topics in the lecture help build long-term retention, so do not be afraid to communicate with this topic. Again, I'm here if you need anything. Thank you.